Okay, sure. Yeah, you can share your screen.
Okay. So there are two proposals that I wanted to talk to the community about today. The first one is related to the concept of workload anti-affinity. I think we had filed um, a ticket asking for some review of this a couple months back, and then I think I created a design document, just like a rough design recently. So I thought it was worth to go over and um, one, talk about if the use case is valid, and then two, maybe talk a little bit about the design choices. So um, to give a brief overview, in Kubernetes, currently it's possible to define pod level anti-affinity rules that the Kubernetes scheduler will take into account. Um, so there is a concept of pod anti-affinity. So if um, you label a couple pods with a similar label, and you would like them to be scheduled on different nodes, that scheduling rule can be honored to make sure that pods are always scheduled to different nodes rather than sharing the same one. And this can be helpful for ensuring high availability requirements. Now, in our case, I can give kind of an overview of two different types of cases that we deal with. So our users primarily are deploying Flink deployments or Flink jobs. And these jobs can have differing tolerance for downtime. So for simplicity, there are a variety of cases, but I think I can kind of boil them down to either high tolerance, which means that a couple minutes of downtime is tolerated. Users simply deploy a single application to our federation, and they're okay with failover taking a couple minutes. And by failover, I mean the time that it takes for Karmada to recognize that the application is unhealthy, the toleration seconds for the failover, and then for the application to be rescheduled and come back up. For applications with low tolerance, we have a couple users who can't tolerate more than a couple seconds of downtime at any moment. And
Mm-hmm.
as a result, what they end up doing is they actually deploy two duplicate applications. So we call that an active-active deployment strategy. So what that means is if we have two data centers, one in New York and one in New Jersey, what those users do is they deploy two identical applications that are both reading from the identical source. They're processing the same exact data, and then they're committing all of that data to the same sink. And they have their own deduplication processes in place to make sure that there are no duplicates in the data. But what that ensures for them is that if one cluster goes down, they have a duplicate application that's doing the same exact thing running in a different data center. And so in the land of Karmada, what we would like to do is we're still going to have these users deploy two applications to two different data centers. But if one cluster goes down, then their other application will continue running and it'll wait for Karmada to reschedule the other application so that
Mm-hmm.
at all times they're running two applications. Um, this is particularly important in cases where we want to do maintenance as well. Like for example, if we're doing Kubernetes upgrades on the cluster, ideally we don't like doing Kubernetes upgrades while production level applications are running on them. So what we would like to do is actually just drain the cluster, have those applications reschedule, and then the tenant still has two active applications running at once. Um, but the reason why this is important is because currently Karmada doesn't really take into account this use case of duplicate applications. And as a result, it's not possible for Karmada at scheduling time to make sure that an application or two applications are not scheduled to the same cluster. So if we were going to take, let's say, a cluster set with three member clusters, and we wanted to schedule two applications there that are supposed to be running in tandem, Karmada can give no guarantees that those two applications wouldn't be scheduled to the same cluster. And if they are scheduled to the same cluster, well, that's not ideal because if that cluster goes down, then the user will have downtime because both of their applications will be impacted. So currently with Karmada, we can get around this. What we decided to do in the meantime is we simply create two cluster pairs. And so one cluster pair is in one geographical region, and another cluster pair is in another geographical region. And we'll have two separate propagation policies whose scope is based off of the label of the application. So if a user wants to deploy two identical applications, they can label their application as New Jersey or New York, and the Karmada scheduler will notice the label and propagate them to their respective clusters. And we create an additional cluster that will allow them to fail over as well in the cases of application issues or if we want to do maintenance on the cluster. However, this requires that the user or that we provision enough resources for almost twice the amount of the total resources that they need. If we had workload anti-affinity, what we could do is simply have a three cluster set and then have Karmada make sure that two identical applications that are labeled with the same label will never be scheduled to the same place, which would bring down our total resource requirement. Uh, any questions on the use case?
Yeah, just to understand, so you mean the two applications are actually relevant with each other, right?
Mhm.
They
Yeah,
they they are not like different services, different system. They are actually logically related with each other. Just that you use two template to define them, right?
correct. Yeah, I wasn't sure how to make it, I guess, very clear here, but essentially,
Mm-hmm.
what the user will do is deploy two duplicate applications.
Mm-hmm.
And
Mm-hmm.
that's simply to ensure that if one application goes down, their other application is constantly processing data. And
Mm-hmm.
meanwhile, they can wait for the other application to fail over and come back up. And I mean, there will be some time that it takes for the other application to catch up in terms of its processing, but
Yeah.
eventually they will realign and process the same data again.
Mm-hmm. I can understand that this picture shows the workaround that without the anti-affinity feature, you
Hmm.
deploy two apps A and app B to cluster A and cluster B. But
Hmm.
if we have the anti-affinity feature, probably you just need to uh, deploy one application and to both class A and class B, right?
Yeah, so if we
Mm-hmm.
support workload anti-affinity, what we would do is instead of using like four clusters in total, we would be using three clusters. And instead here, I mean, currently
Okay.
Karmada could potentially schedule both those applications to the same cluster. But what we
Mm-hmm.
desire is that um, Karmada will schedule these workloads to different clusters. And so this gives us the assurance that even if something happens to cluster A, or if we're doing maintenance, or if something happens to that application, Karmada
Mm-hmm.
will eventually reschedule this workload X to cluster C, and it
Mm-hmm.
won't reschedule it to cluster B because that's where the other duplicate workload is running. Um, but in total, that it just decreases the resource footprint for us, since we don't have to um, have a duplicate fallback cluster for each workload.
So for the left part of the workload X, it should be workload Y, right?
So workload X and Y are the duplicate applications. So
Mm-hmm. Yeah.
they're both processing the same data. And if something happens to cluster A, what I desire
Mm,
for Karmada to do is, okay, it'll reschedule the application, and it'll actually filter cluster B out of the feasible clusters because it'll notice that there's a workload already scheduled on that cluster with the same label, like spread across clusters, for instance. Um,
I get it. So if it's easy for me to understand if you um, name the left workload with workload Y, because I think
mm,
uh, the workload in cluster A just a copy of a workload Y, and
okay,
the workload in cluster B is actually another copy, right?
that's correct. Yeah. So I can make that more clear.
So,
Um,
have you checked that actually so I think this is important because you are currently basically using two templates, right? Duplicated uh, to define the copies of an actual application. Have you take a look at the propagation policy because we also have a mechanism to support an application being deployed in a duplicated mode, and also
mm,
with the cluster. I remember we have the spread constraint. Actually, we support like users to indicate the minimal clusters, number of clusters. I remember. Yeah.
mhm.
Does that uh, meet your requirement, or what are the gaps?
So we could try using the duplicated scheduling strategy. The pushback that we received from some users is
Mhm,
it's not just that the application, I mean, the application itself, what it's doing is duplicated.
mhm,
But since users applied two different applications, they've actually also edited the sources and some of the configurations in the Flink deployment to be co-located with the Kafka source that they're ingesting from. And
mhm,
so if we decided to just duplicate the Flink deployment, what could happen is you could have a Flink deployment that's scheduled to the New York side, and then it's
mhm,
ingesting data from the New Jersey Kafka source, which uh, potentially isn't that bad, but it will cause some latency when actually ingesting data into the pipeline. So that's just the one concern that we had. I could double
mhm,
check if that's something that we could do though, because that would make I think this a lot easier.
mhm. Yeah, I think it's very important. I mean, and also very valuable if you can, compare the two approach. The
Hmm.
current one you are presenting actually, uh, users use different template to define the different copy of a actual application, right? The other hand, the other approach I mentioned is that we use one template. I
Hmm.
can imagine some of the difference is that using multiple templates uh, give users more flexibility to control for example, you mentioned about the configuration and also the other, maybe later on about versioning sort of things, right? That
Yeah.
give more flexibility. And I think it's very important and valuable, to write them down. So also, I think it's very helpful to give others the
Mhm.
background and understand maybe they should not try the simple template one, the approach. I mean, yeah.
Yeah. I can try that out, and
Mhm.
I can write down kind of the
Mm,
differences or the gaps between the two strategies. Even just thinking off the top of my head currently, the one issue I see with using the duplicated strategy is that Flink deployments are essentially the source of truth when you want to either control the life cycle of a specific job. So you use the Flink deployment when you want to either suspend the job or restart it. And that includes restarting applications from a specific state. So
Mhm.
if, let's say, in the instance in which we apply two applications to different clusters, if one application gets into a non-recoverable state, if we were using the duplicated strategy, we would have to edit the Flink deployment to cause it to start from the latest state that's valid. And that would actually
Mhm.
propagate to both applications. So you couldn't control the life cycle of individual applications using duplicate, um, which that might be the
Yeah,
one issue.
yeah, yeah, yeah. Yeah, I think that's a very helpful information. Yeah, and also for the other, later on users, they may also think about the best practice to define their applications. Yeah.
Yeah. What I'll do in that case is just for the sake of looking at the differences between the duplicated strategy and this, I'll create a document with kind of background on what the
Mhm.
differences are and what some of the gaps are. Maybe that will
Mhm. Mhm.
provide more
Mhm.
background here.
Sure, sure. Yeah, so for the current approach you are presenting, would you like to go ahead? Just yeah, maybe we can also take a look at the rest part.
Okay, sure. In terms of, I guess, the proposed changes, a lot of this is just based off of the pod anti-affinity feature in Kubernetes. Um, so a lot of it is sort of one-to-one. But what we would essentially change is within the propagation policy, we would introduce a placement, which would include workload anti-affinity, and maybe eventually workload affinity if that's necessary. But this workload
Mm.
anti-affinity would include the required during scheduling, ignored during execution definition. So we would essentially have a strong enforcement of these scheduling rules to make sure that workloads are never scheduled to a cluster that already has a duplicate workload. I left the other um, scheduling type unimplemented, the preferred during scheduling, ignored during execution, just because it's not necessary for our use case. But this follows using just like a workload affinity term. So this is similar to the pod affinity term in Kubernetes. So you would have a label selector that's selecting for a specific resource for the namespaces that it's listening to, as well as the topology key and namespace selector. Um, so this is just taken almost one-to-one from the Kubernetes pod affinity rules. So I think the biggest challenge here is how do we efficiently track whether or not a cluster has a workload with these anti-affinity rules scheduled onto it. Um, so again, kind of borrowing from Kubernetes, I think what we need to do is essentially improve the existing cluster info and cluster snapshot objects to have a bit more information, specifically to include anti-affinity information. So the existing cluster info only contains a pointer to the cluster object itself. But in order to have like the snapshot be able to track clusters that have workloads with anti-affinity rules scheduled on them, we would actually have to expand it a little bit to include bindings with required anti-affinity. So the resource binding itself would have a pointer to whether the resource has anti-affinity rules. Um, And so that's kind of what we would use. This includes the cluster snapshot. So currently the cluster snapshot only has the cluster info list, which scheduler uses to determine your feasible clusters when scheduling. But in order for the schedule to filter out clusters that might violate anti-affinity rules, we would need to start keeping a list of these anti-affinity workloads. So here, in order to make it more efficient, we could use like a cluster info map just for faster cluster info retrieval. And in the Kubernetes node snapshot, it's actually implemented using a doubly linked list. So it would allow for us to have quick retrievals, but also ensure a way to actually track the nodes that have been updated from the last snapshot using a generation. So we would be looking through the existing doubly linked list and only updating clusters that haven't been updated since the last generation. In addition, I think we do have a cluster cache currently, which is created during the scheduler init. But currently what it does is it actually just fetches all of the clusters that are registered against Karmada. And so this may need to be improved as well. As for the scheduler, currently it does have an internal cache. Let's see here. Which, again, this is what's generating the cluster snapshots. But this snapshot is just fetching the existing clusters that exist on Karmada. And so for this, we would just have to augment it to include also anti-affinity rules. So whenever a new scheduler cycle would begin, we would update the existing cluster snapshot with any potential updates that had occurred to the clusters. So we would need to essentially maintain that information. We wouldn't be able to just fetch the new clusters each scheduling iteration. And then lastly, we would need some sort of filter plugin. So in order to filter out clusters that violate the workload anti-affinity rules, we would have to add this plugin, which could check each cluster and determine if it satisfies the workload anti-affinity, just based off of the matching topology key. So any pending workload that's attempting to be scheduled that conflicts with anti-affinity counts that are already on that cluster, we would filter out that cluster during the scheduling step. Yeah, this is pretty high level, so apologies if I wasn't very, I guess, clear. But yeah, let me know if there are any concerns or if this isn't the way that we would want to go.
Yeah, I think first of all, I would like to discuss the API part. And actually, I developed the pod affinity and the anti-affinity. So I'm quite familiar with that.
Oh, amazing.
Yeah, yeah, yeah.
Well,
And
thanks for
also,
taking the time.
you can see, I'm kind of thinking, especially, I'm not sure if you have tried out this featuring in one Kubernetes cluster. I mean the pod affinity and affinity. So my feeling was that actually, the required during scheduling, ignored during execution. This is kind of long failed name, right?
Mm,
Yeah, and yeah, there was some design consideration in that period of time, so we finally decided to use uh, such a long failed name. And also the second thing is actually you can see the term. Actually, we are kind of have a little bit nested. It's like two level because we want to support like ended terms and or the conditions.
mhm.
So I'm not sure, especially from a user perspective, is it too complicated for configuring this API.
Yeah, that's possible.
Yeah, and also later on, you know that in Kubernetes, the other contributor also introduced the topology spread constraints. So
Mhm.
uh, have you take a look at that? So I mean, just from the API perspective, from the configuration perspective, if you can provide some feedback on this, and also maybe reach out to your, you know, the internal customer, whether
Mhm.
they prefer which one. I think this input are also very important.
Yeah, sounds good. Um, Topology, and it's just topology spread. That's the feature. Okay.
Yeah. Yeah, and also the second thing I think this time I will try to be careful introducing affinity between workloads because anti-affinity you know uh it's uh it's less expensive than the affinity inside of the scheduling period because when you are doing a affinity check, you need to almost completely uh, you know check all the workload to find out whether any binding or any scheduling result meet the affinity requirement. But for anti-affinity, you only check the target resources if there's any uh, kind of replicas or workload already there, you want to avoid collocating. Yeah. So
Yeah, makes sense.
affinity is uh, you know, cheaper inside the scheduler, and also there are more requirements about the anti-affinity. Yeah.
Mhm. So anti-affinity is less expensive scheduling wise than affinity. Okay.
Yeah,
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 makes
yeah.
sense.
And also from the high level, I think later on, if we want to introduce affinity, we maybe a possible approach is we have a higher level abstraction uh, to kind of indicate that. So, and we can also maybe inside the class inside the scheduler to deal with that high level abstraction that uh, might be helpful for more efficient implementation. I mean the scheduling algorithm.
Yeah,
Yeah.
makes sense. Okay. Um, I guess, is there anything here that raises any red flags in terms of like the idea behind the implementation? I mean, um, it is borrowing very heavily from the Kubernetes implementation, so it's pretty similar.
Yeah.
Okay.
Yeah. So the algorithm part, I think that's fine. It's more about the API structure uh, to the users. Yeah.
Okay.
Yeah.
So I guess what I'll do in that case is outside of the other document that I'll create, documenting the differences between the duplicated strategy versus workload anti-affinity, I'll also ask tenants about what they think in terms of what would be easier to configure, whether it would be anti-affinity terms or using just the topology spread. So
Mhm.
I might just include that all in one as user feedback, and then I can share it with the community as well.
Yeah. Yeah.
Okay. I just read a notes on the meeting notes. Mihash, can you go back to the meeting notes?
Yep.
Yeah.
Not this.
Kevin, you just mentioned that we probably need to consider another approach that use the spread by constraint, right?
Yeah, I think that's a possible option. So I would
Yeah,
like to know, especially from the user perspective, what are their consideration, when they are investigating the two approaches, and what are the gaps and their
yeah,
uh, uh, considerations, and also what are they mainly care about? Yeah.
yeah. I got it. So okay, sure, good. I can run a test. Probably this a good chance to for us to enhance the spread by constraints. Okay. Shall we move to the next?
Yeah, sounds good. So to give a brief background on this was something that we had brought up, I think maybe a while back. But essentially, let me go over the design doc. So our use case here is primarily the way that the federated resource quota interacts with failover. So since our applications are expected to migrate between clusters, it's really up to us as, I guess, the owners of the platform to make sure that each cluster has sufficient resources to be able to run and host those applications. And what we believe is that actually enforcing those resource limits on the Karmada level will simplify the way that we manage our resource quota. So the existing federated resource quota provides a way for Karmada users to just manage their resource quotas via static assignments. So if you define a total federated resource quota footprint and you subdivide that total amongst the existing member clusters, and this is simply to save you some time instead of having to create a bunch of propagation policies specifically for resource quotas. However, I think that this feature was created before we added in more of like the application or like stateful application features. And it doesn't work entirely with failover. So since static assignment requires that the users subdivide their quota between clusters, each member cluster's resource quota will be less than the total quota that's been allocated to the user. So what this means is that you can run into issues where the user has used up all of their quota, and yet they still expect failover to occur. So in cases in which like a cluster goes down or an application gets failed over, the other member clusters in that case will not have sufficient resources to host those applications. So if we take a look at the existing federated resource quota behavior, we have these totals where we have a total CPU requirement of 40 and a total memory limit of 50 gigs. And we've evenly assigned resource quotas between these two clusters where we have 20 CPU and 25 gigs of memory. Now, assuming that the user has applied all of their resources to their namespace and they're using the max amount of resources, since these are static assignments, if you ever try to fail over, none of the resources that have failed over will eventually be scheduled by Kubernetes or actually even be accepted because all of those resources will go above the resource quota that has been set statically. So for example, in this case, the user has 40 CPU, they expect to have sufficient capacity for failover as well. So what would work is if in the above example, we kept the 20 CPU and 25 gigs limits on each cluster, but we actually set the same limit on the Karmada control plane. So that way, the user is limited from the Karmada control plane level to only use that total amount of CPU and that total amount of memory. And then whenever a failover occurs, the user will be sure that their other cluster has enough resources available for their application to be failed over. Does that make sense so far?
Actually, can you scroll out your screen?
Oh,
I
scroll up.
mean, zoom in, right?
Oh,
Zoom
zoom
in.
in. Yeah.
Zoom out, yeah.
So yeah, what's happening here is we've statically divided the total quota into two, and each member gets 20 CPU and 25 gigs of memory. But the problem here is, given that we're actually propagating these resource quotas to each member, whenever there's a failover,
Yeah.
the resource quotas won't be updated. And so failover will fail because the other cluster is completely filled.
Yeah.
So
When doing failover, we didn't update the resource code. Basically the resource code in each cluster, right? So it runs into the situation that the healthy cluster may not having enough quota to spin up
Yes.
the rest of the replicas. Yeah.
um, so I guess there are two ways about going
Mm-hmm.
about solving this.
Mm-hmm.
The first is, in my opinion, a bit simpler to do, which
Mm-hmm.
is given that the federated resource quota already defines an overall limit, we could create essentially a way for Karmada to actually enforce those limits on the Karmada control plane itself
Mm-hmm.
via a custom controller that kicks in by default to track the overall usage, as well as an admission webhook that would actually block users from applying or updating resources that go above those limits. Or we could decide to make the assignment of the resource quota dynamic. But I was thinking about the dynamic assignment, and it seems a bit difficult. I didn't spend too much time actually thinking about a design there because we actually have our own internal commit that does the overall resource enforcement. Um, so I thought if that's already implemented, we could at least go over that and see if the community would be open to using that instead. But essentially, the way that we go about doing it is the resource binding spec would change to include a federated resource quota reference. And so for us, this gets just updated by default. But what could happen is we could either check if there's a federated resource quota in the namespace and add it to the binding by default, or if the federated resource quota has a scope, which we would have to also add to the API if we wanted to. Given that scope, we could determine if the resource matches the scope and then add a pointer for the quota in the binding if needed. So this would simply be a pointer to the federated resource quota of the namespace. For the controller that we're using, the controller reconciles whenever a resource binding is created, updated, or deleted, but only if the resource binding has a federated resource quota definition. If it's not, then the reconcile will skip. And what the reconcile logic currently does is the controller will fetch a list of relevant resource bindings for the namespace and add up their resource requirements. This isn't entirely ideal because it is grabbing all of the resource bindings by the namespace each time. But we could improve this by just calculating the delta of the given resources or the given resource, and then updating the resource footprint that way. And then the two additional changes, one from the scheduler side. So given that the controller for the overall usage is listening to role bindings or resource bindings, the federated resource quota will be calculated after the resource has been created or updated. So if a user bulk applies a bunch of resources at once, it is possible for the user to go above the quota limits. So what we would have to do is check on the scheduler to make sure that before we actually schedule the resource, that the quota is honored before deciding to schedule it. And then finally, we use an admission webhook. So we do two things. We edit the existing federated resource quota validating webhook to prevent users from toggling static assignments while the resource quota is already in use. This is just because static assignments and the overall limits have different controllers, and so we don't want both of them reconciling the resource at once. And then two, we create a validating webhook to enforce limits. So what this does is it uses the Karmada default and third-party resource interpreters to calculate the delta in resource usage for the quota. And if the applied resource goes above the limit, then the webhook denies the request. And this has been working pretty well for us so far. But obviously, we want to align with the community in terms of what the best way about going about this is. So if you have any concerns about this strategy, or if you'd rather us take a look at a different sort of approach, that's sort of what I wanted to get on the same page on.
Yeah, thanks for bringing this up. Actually, I remember in the early days when we are discussing about the resource quota design, actually we think there should be different approaches implementing the quota management in the Karmada level. So static assignment is just a very simple way for users, especially they just want to, from the federated control plan to config the member cluster quota implementation. And also this way, it's also very easy to, work in the situation that HPA enabled in the member clusters. Yeah, I think for the approach you presented, actually we also discussed a bit in the early days. So the major requirement for users in this approach is that basically all the quota, validation and enforcement need need force all the request to go through the Karmada API server, right? And and also if the HPA enabled in some of the member clusters, it will cause the actual replicas go beyond the go above the replicas designed in the template in the Karmada layer. Yeah. I think that's the one of the requirement or limitation in usage. Yeah. Yeah, but I think this approach is also valuable because it brings more flexibility among the different member clusters, especially when uh, users need failover mechanism between member clusters. And a third approach is kind of a unified checking of a quota evaluation validation. It's like uh, every member cluster they goes to a unified point to check the quota, basically the quota consumption, and that part is more, more easy to make sure no workload in the member cluster exceeds the overall quota limitation, but that requires the network between member clusters because all the member cluster API need to call the webhook to a certain location to check the total quota. Yeah.
Yeah, my because I know that there's I think a comment under the existing federated resource quota API definition that discusses the dynamic assignment. The one concern I had with the dynamic assignment is simply whenever an application fails over,
Mhm.
which we don't know how often that could be. We don't assume that it would be often, but it can happen. In that case, before the application can be rescheduled, you would always have to check that the resource quota on the destination is sufficient. And if it isn't, then you would have to update the resource quotas before the scheduling step takes place. And so to me, it potentially feels like it could be rather expensive to do. But
Yeah.
um, that's why I kind of preferred having the overall limits because that way we just set what the limits are on the Karmada level, and it's up to us as platform owners to define what the cluster usage is or what the cluster available resources are. Um,
Yeah. Yeah. I agree. Yeah. So I'm thinking maybe we can also uh I think we have a kind of document mentioning there should be multiple quota approaches, right? I don't remember the exact path, but I think we mentioned somewhere. So we can I think we can add this approach you presented here also to become one of the option, and the users can choose according their requirement. Yeah.
is the document that you're referring to just potential other approaches that haven't been implemented yet, or um,
I remember actually in the early days when we discussed about the quota management mechanism, we first of all mentioned that there are multiple requirement, and some of the requirements may be different from the different end users. They want, I mean, the way they wanted to manage the quota setup in a multi-cluster system, and obviously the static assignment only deal with part of the issues, right? They
yeah.
have it have its own limitations, and I think the federated resource quota you presented here is also approach uh, to deal with some of the issues, but it also have some requirements of I mean the limitations of the usage. Yeah, so I think it's very important to added this approach to the overall introduction of the multi-cluster quota management document, and then you can just go ahead to describe details about how people would use the federated resource quota approach. Yeah, you presented here. I mean.
Okay, understood. I think for us, the way that we have our users define their resource quota is we have an external syncer that essentially translates their requirements, their CPU and memory requirements into a federated resource quota object.
Mhm.
Um, so that syncer actually generates the federated resource quota for each of our users' namespaces. And it automatically gets updated if they ever require more resources or if they dial them back.
Mhm.
But for us, given that we are using the failover feature pretty consistently, we simply want to um, gate it at the Karmada level so that we don't have to do any sort of
Mhm.
calculations
Mhm.
when the failovers happen. We treat each member cluster as sort of identical.
Mhm.
Um,
Mhm.
yeah, but okay. Thanks for the review. I suppose I can add this to the document that you were referring to. Either maybe you can share it or Honkai can. Um, but I guess in terms of next steps, what should we do in terms of kind of coming to a consensus as to um, what we want to do with the improvements?
Yeah. Mm. So you mentioned there will be some of the maybe new webhook or admission controller introduced to implement the quota tracking, right?
Yeah.
So yeah, I would like to know, or maybe we don't have the detailed data, but we do need to consider the latency trade-off when enabling this feature. Yeah,
Okay.
I remember in also actually in Kubernetes, enabling the quota feature, costed uh, some increasement of the API latency. We need to think about that. Maybe we can do a test after implementation done. Yeah.
Um, So what I could do is since like the implementation, at least from our side, is complete, so we're
Mhm,
running it
mhm,
on kind of like a fork of upstream. Do you have a
mhm.
recommendation on how we could test the latency increase? Is there any sort of tool that you would recommend?
Yeah, that's a good point. Hmm. I don't have a recommendation so far. Yeah.
Okay.
Maybe we can take a look what I mean the early days how Kubernetes test the API latency.
Okay. I could probably take a look at ways we can test it as well, and maybe I can publish the results.
Mm-hmm. Mm-hmm.
Yeah. Are
And also,
there
I'm thinking another option maybe, maybe we don't implement the admission in the webhook way. We implement as a entry uh, plugin admission, make it configurable whether users want to enable or not or disable it.
Oh, so like a toggleable admission webhook.
Not webhook, just the admission controller.
Okay.
Yeah, because webhook it's a remote core. Yeah,
Yeah.
yeah. Tongkai, do you have any comments, opinions on this?
No, actually, I didn't follow your discussion very well.
No,
So,
actually, in the early days, admission is most of the admission. Actually, our admission controller, it's just some piece of code in the main repo of Kubernetes. Later on, there are a lot of new requirement to extend the admission controller. So the Kubernetes community introduced the mechanism called the admission webhook, so people can enable uh, their own remote admission controller, basically. But that rely on the remote API call, so actually it uh, takes more time, right?
right. Uh, that's the reason the Kubernetes tried another approach named CEL pattern, right? That
Mm-hmm,
that
mm-hmm,
user can define validation rules in the server side, so that
mm-hmm.
it can avoid the remote call.
Yeah, so I would suggest in the first stage we can still go ahead with admission webhook because that's easy way to implement the functionality, and then maybe we can if we can have some test or get some data about the latency issue, we can
Mhm.
dive more into more details of whether we should go with the server side admission. Yeah.
Okay. So how about I create a proposal PR, and I'll include um, a little bit more details specifically about the implementation, and then also I can add some trade-offs between using the webhook approach versus the admission controller, and maybe provide some uh, actual figures there in terms of latency.
Yeah. 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 That's
Okay,
very helpful.
all right, sounds good. Thanks so much for your time. I'm sorry that I took up the entire hour, but I really appreciate it.
No problem. Would you mind would you mind to write some notes about what we are gonna do to uh, move the feature to, from this meeting? What we are, list some actions.
Mhm. Let me list down, I guess what I'll do is publish a proposal document with clear implementation details,
Yeah.
um, as well as trade-offs between, say, admission, webhook, um, versus controller. Um, So yeah, I'll take a look at that and we'll let you know when I publish the proposal. But hopefully I can do that soon.
Okay. Okay, sound good.
All right. Thanks so much.
Okay. Then goodbye. See you next time.
Yeah. Take care.
Take care.
Yeah,
Thank you.
Bye.
take
Bye.
care.